Thank you, Gerwin.
Thank you for the introduction. Why is the verification guy giving a talk about tests? Yeah, it just kind of happened. Also, they're important. We need them. In fact, that's why do we need tests at all, right? So we have formal verification, but as June said, we have assumptions.
I'm sorry, it doesn't work.
Oh, it doesn't work. Okay.
Yeah.
I think you have to
share the other screen.
I'll restart that then.
and then go into.
That's still on the same slide, so that's good.
Let it go.
Okay.
Yeah.
Um,
Can you see now?
Yeah. Yes.
Yeah.
Okay.
Cool.
Thank you so
Perfect. So we're still on the question why are we testing here? So we do have formal verification. Point one is, as June said, the formal verification has assumptions, and we want to test those assumptions. So that is number one. Number two is, it's not just the kernel. Like the foundation manages over 60 repositories. In my abstract, I had 55. I just looked. I guess the difference of 5 is archived repositories. So about 55 are active. And the kernel and the proofs are just 2 repositories of those. So what else have we got? We have like seL4 test, seL4 bench, we have a whole bunch of libraries. We have the CapDL language, the initializer, we have camp keys, we have VMs, we have the websites, we have the test infrastructure itself, the tutorials, and so on, so on, and so forth. All of these need to work. Only the kernel and the system initializer have proofs. The rest just has tests. So they need to work, but they also need to work together. So, you know, version 1 of CapDL is not going to work with version 12 of the kernel. They have to fit. So this kind of leads to the following questions, or at least these are the questions I'm going to vaguely answer in this talk. You first have to know which repositories you need for a specific task. So if I want to test seL4, out of the 60, which ones? Do I download all of them, or what do I do? And then if you've answered that question, that's actually not good enough. Like I said, you need to know which version of what goes with which tests. And then once you have it working, how do you ensure that it keeps working? The which version of what is the thing that some people grumble about are these manifest repositories. These manifest files come from the Google repo tool, and it is a tool. It does what we need it to do. It comes from the fact, like I said, that the kernel is never used in isolation. You need sets. And the requirements for these sets is, okay, I need to record a set, a list of repositories. I need to record what version of which repository. And I need to be able to manipulate that information itself in version control, because it's going to change over time. I would also like, in addition to those requirements, I would also like to be able to say this specific set of repositories at this specific configuration worked. But if you want to do development, instead, don't use these versions. Instead, use these branch names. Because if I'm going to develop, I'm not going to branch off 10 revisions earlier. I'm going to work on the head revision, even if maybe that head revision doesn't work right now. Okay, so here's an example of the seL4 test manifest repository. And really, there's only 3 interesting files in here. The thing that you get if you just check it out, if you follow the instructions on the website, is default XML. And that's the one that records exactly which revision of what worked. It has a bunch of more information under which path to put something and so on and so forth. But the important information is the revision hashes. And if you look very closely, let's see if I can do that with the cursor here. I cannot. This is back to the beginning of the slide. You can see it a bit better here. This is being updated by the seL4 CI bot. And it's updated fairly regularly, like every few days, whereas all the other stuff is old. And that's how it's supposed to be. So these working versions are updated every time the tests pass. These development versions, they just mention path, branch names and path names. So they will say, use the master version of seL4, use the MCS version of the proofs, use the whatever version of the tests. And if you develop, then that's what you want to do. Okay. If we're looking at this kind of collection, it helps to name two concepts. I'm just going to call them local and global consistency. Local consistency is basically if I take a single repository and everything in it works without looking at the context of where it is. So in terms of tests and so on, the things that I would look at are like code style and do all the links in the repository work, like just web links and so on. Does the code compile on its own without needing to pull in other repositories, or does everything have a license and so on? These are local checks, and they should always work, basically. The other one is global consistency, and that is basically all tests where I need to draw in an entire set of repositories. So if you want to think about it in terms of tests, every manifest repository is going to have at least one set of these global tests. For instance, proofs or seL4 tests or the benchmarks and so on. So as I said, we always maintain local consistency. For global consistency, you could try to do that, but it turns out that is very expensive. Sorry. So why is it expensive? Well, first of all, it's going to be a lot of tests, multiple repositories, a lot of code, and so on. It's not always possible to always maintain global consistency because you might have two changes in two repositories. And there's going to be at least some point in time where only one change is visible. So the best that we can hope for is that we find out quickly when it's broken and that we fix it. And so that's the policy. So locally, every pull request, everything we do has to maintain consistency. And globally, if we break it, we should fix it immediately. So in terms of implementation, if you've ever made any contribution on GitHub, you will see that all these local tests run on every pull request, and they will report immediately back, or well, immediately after they've finished, if something doesn't work. And about, not all of them, but many of them are actually required for the merge button to be enabled. So some of them, for instance, the link check is, in a sense, up to the person who merges, because it might just be some website is down for an hour somewhere. Who cares? It's okay to merge anyway. We want to know about it. But if the code is not signed off, for instance, nobody is able to merge it. Okay, for the global tests, usually, like I said, what we have is for each manifest, for each collection, there's one global test. They're usually not triggered on pull request. There's some exceptions for the kernel itself mostly. And instead, they're triggered when the manifest changes. And the manifest changes when you have merged a pull request somewhere. And if that manifest if a repository has changed and all the global tests pass for that repository, then this default XML is automatically updated. So default XML is the thing that you get when a test has passed, basically. There's a kind of funny wrinkle that is due to GitHub. You would expect these global tests to live in the manifest repository because that stands for the set, right? But GitHub is a very, how should I say? It's very single repository oriented in its test setup in these GitHub actions. So it will only show you the result of tests for the workflows in your repository where you're just making the pull request. So it's actually much more convenient, for instance, for seL4 test to run in the seL4 repository so that you see the results immediately, because what you're focusing on is seL4, not the test repository. Or for seL4 bench, you would look at the seL4 bench repository, not at the seL4 bench manifest repository. Do not despair. There's a file that says exactly which test is where and what is triggered for each manifest, basically. Okay, so I mentioned GitHub Actions a few times already. That's how it's implemented. I'm not brave enough to click on the link right now because I don't know what's going to happen with the screen sharing. But you can go to this repository and you can see all the individual actions that are there, and you can actually just use that code yourself in your own test setups. This is the content, and these .github workflow directories that you see in pretty much every foundation repository. This is how these actions are called, by what they're triggered, and so on and so forth. Almost everything runs directly on GitHub, which is it's basically backed by Microsoft Azure. Apart from two things, the things that are too expensive to run because they take too much time, they run on AWS. And things that need real hardware, like the boards that seL4 runs on, they currently run on the machine queue at UNSW. And one of the cool extensions we could maybe do is extend that to other institutions, if somebody's interested. Okay, so that was kind of the theory around all this. What tests do we really have? There is an overview page. Don't worry if you don't know it. It has been existing for about a week. I made it because I thought it would be good to have for this talk, and in general. Again, I won't click on the link, but this scrolls down quite a bit. So this will have all the tests of all the repositories. It has a summary line up here that has sort of the main important ones. And then it has all the tests of the important repositories. And then it has just a list of all repositories. And yeah, maybe slightly interesting. You can see currently pretty much everything's passing. Prepare binary verification is failing. Hi, Matt. It's actually failing on a timeout because it takes longer than 6 hours to do the RISC-V -02 thing, and 6 hours happens to be the hard timeout for GitHub, which means we probably have to port this to AWS at some point. But okay, currently everything is well in the universe, I would say, or almost everything. So what are these main tests? So you know seL4 test. It's the thing that ends with all is well in the universe. If we run seL4 test, when I say we run seL4 test, we actually run seL4 test a few hundred times. We run it for every combination of configurations that we have, like MCS, non-MCS, hypervisor, non-hypervisor, SMP, non-SMP, 32-bit, 64-bit, whatever else we have. And this is all, times. So we run these on simulators for all of the main hardware architectures that we support. That runs first. And then if that succeeds, we run it on all of the boards for which seL4 is supported and that we have at UNSW. Again, each of the boards is going to run all of the configurations. So this takes quite a while to finish. It also happens to exercise a whole bunch of the basic user level libraries, which is a nice side effects, because they don't have any other verification or assurance apart from being run in those tests. Okay, the proofs are just the proofs, the full proof suite of seL4 of everything. Proof sync is a very quick and small test. If that is red, it doesn't mean that the proofs are not working. It just means that the proofs are lagging behind the head revision of the seL4 development version. So it means it's work for the verifiers to do. It's something we want to know about very, very quickly. seL4 bench is the thing that, runs the benchmarks. It will leave the results behind on GitHub, but it will also update the website. It exercises a bunch more of the user level libraries, so that's good. The one that's really doing all the user level stuff are the camp keys tests. So this runs camp keys, it runs the system initializer, it runs capdl, it runs a whole bunch of user level components and applications. It runs them both on simulators and on hardware. It runs them on fewer hardware boards, not on all of them, because that would just be too much and take forever. Yeah, so this exercise is mostly the user level stuff. And then CampKeys VM, that's the virtual machine monitors that we have. I should probably also mention the tutorials. They also run They have their own manifest. So if we update the kernel, we will know when the tutorial solutions don't work anymore. A question? Yes, please.
The VM tutorial isn't CI, and that's the one that people try to use the most of.
All right, let's get the VM tutorial in CI. I think people online might not have heard Kent, so he was pointing out that the VM tutorial is not in CI, and that's one of the most used ones. So yeah, that would be good to have there. I'll take pull requests anytime. Okay, there's a set of mandatory tests that are actually mandated by the foundation for any contribution to the seL4 repositories. There's a whole page that describes them, so I won't go too much into detail there, but there are things like code style and gitlint and having to have license headers and so on. It's not going to check that you use the right license. It's just going to check that you declare a license. So if you review it, you should check that it's the right license. Yeah, it's the thing that you see, like if this is a pull request, at the very bottom of the pull request, there's going to be a list of things that have a green tick or say succeed or not. If you zoom that out, that's here. If it fails, there's a little link called details. You only get to see this when you're signed into GitHub. So if you're in guest mode, it won't show it, but if you're signed in, you don't have to be a member of the organization or anything. You should be able to click on details and then see the logs why it failed. I've tried to make all the logs visible directly on GitHub so that you don't need to download stuff and can tell fairly quickly. I'm sure it can be improved. Again, I'm happy to take pull requests. One thing that I tend to miss myself a lot, if you want to see more details, there's actually a whole tab called checks on the GitHub UI for every pull request. So for an seL4 pull request where I enable all tests, that case goes about 89 or something checks. And each of them is actually a collection of checks, so it's extensive. Okay, 2 example repositories. Let me check timing. I'm going to do mostly one of them, I think. Let's take the seL4 kernel itself. It has the strictest set of checks, the mandatory ones, plus a bunch of local ones that are fairly easy and quick. So a compile check is just, for a whole bunch of configurations, it just does the kernel compile. If it doesn't compile, don't expect a review. Fix that first. It'll build the reference manual, see if that still works. It will check for all the XML files that they conform to their DDDs. The cparser check is the check that the C code that you've contributed fits in the verification subset. So the verification can't deal with all of C, only with a subset, and this check will tell you if you're violating it. If this check is green, it doesn't necessarily mean the verification can deal with it. This is just a screening check. So these are quick and easy. From the other end, the more expensive ones, well, the main expensive one is seL4 test. So for any change on seL4, it will run the full test suite. It will do the proofsync check. And then if all of this has succeeded, it will, well, actually, this one doesn't have to succeed, but if all of the rest has succeeded, it will trigger the global tests of all manifests in which seL4 occurs. And that is all of them. So it will, once seL4 test works, it will go to seL4 bench, CampKISS, CampKISS VM, tutorials, and so on. It will kick off all of these concurrently. And, well, we get enough GitHub runners for this to actually work, so that's fine. So GitHub is actually kind of nice. It gave us a pro plan for, what is it called? Non-profit organization, basically. Which is very useful. Otherwise, you have like 20 concurrent runs, and even one pull request would already exhaust that. All right. So in addition to all of these, on every pull request, you will automatically get seL4 test sim. So this is just seL4 test on the simulators, because that's cheap and can run concurrently in the background. You'll also get this pre-process test. It's basically the same as proofsync, but it runs before you do the change. The idea is if this check succeeds, you can be sure that the proof will succeed. Because what it does is it takes the AST of the entire kernel under all the verified configurations and checks that against the AST after your change. If it's equal, then you're fine. If it's not equal, the proof may still just work because automation might be able to get over whatever change you did, but you need a more expensive test to check that. And these more expensive checks are basically 3 of them. They're expensive enough that we don't run them every time, but you can trigger them manually by adding a label to the pull request. And it's kind of a neat mechanism because adding a label is a privileged operation, so you need to be at least a member of the organization and in the reviewer role to be able to do that. So what the reviewer role really is it enables you to spend foundation resources on more expensive tests. Which ones are there? First, you can build the kernel in the seL4 test image for all the hardware platforms. It's going to take some time. And it basically gives you confidence that if you screw around with configurations a little bit and things like that, that you haven't missed any combinations that are relevant. Then you can just run it. This takes pretty long. But yeah, that will be the full prediction of what seL4 test will say if you merge it. And finally, the proofs. That will take, depending on your change, about 2 hours or so. So this is actually a subset of the proofs. It's the subset of the proof that is, how should I say, that is sensitive to changes in the C code. So other proofs are, for instance, the security proofs are, for instance, just about the abstract specification. If that doesn't change, I don't need to rerun it. If the C code changes, I need to rerun the C proofs. So it's the subset that is affected by that runs here. So that's why it's a bit faster than the full proof suite. If that is green, you can be sure to merge it and the proofs will still pass. A kind of neat little feature, because these are global tests, so they run on manifests. You can make simultaneous pull requests, and you can say, give me the state that I would have if I would also merge this one. And so that's often necessary, for instance, when you change the kernel API a little bit. You might need to change some libraries. You might need to change seL4 test itself. And you'll, of course, also need to change the proof setup. So you can do all these changes and tell these tests, use these pull requests, and pretend they're merged simultaneously. And what that gives you is the confidence that if I merge them one after the other, the global test might be broken in between, but if I've reached the last one, it'll be okay, basically. Okay, so this is an example of what you see when you do seL4 test hardware. So it first builds everything. So this part up to here is in parallel. When it has done that, it will start all the machines. If you scroll down, that's a lot of scrolling. And each of them runs all of the combinations. And if you look inside each of them, that is a full seL4 test. Okay, I'll do this one a bit faster because we're almost out of time. The proofs are the expensive ones that need AWS. It's fairly beefy machines. So these are VMs with 16 virtual cores, 32 gigs of RAM. We usually run 5 of them in parallel for each pull request. They're not all, so for each, the 5 are for each architecture, basically. So one runs for ARM, one runs for RISC-V, one runs for x86. And since we don't have the full proof stack for each, they're not all quite the same number of proof sessions. So the longest one takes 4 hours. The shortest one's probably done in 1 hour. But it's still quite a lot of compute hours. We've put a lot of work into caching for these because we don't want to burn the planet with just proofs and also not the foundation budget. And it will leave the full Isabelle build database afterwards for you to look at. So you'll know timing, you'll know exactly what it did, and so on and so forth. All right, I'll skip over that bit. This is a typical successful run. So again, this will scroll quite a while, but yeah, here are all the proof sessions, basically. What does it leave behind? Or what can I do with it?
Just to clarify, you got to 1045. So.
Yeah. well, plus, right. Okay, in that case, we can talk about this in a little bit more detail. Yeah, thank you. What can I do with these tests? So first of all, kind of neat thing is that all the tests that don't need privileged action will actually run, they'll be fully working on your own forks. So if you fork seL4, and if you just fork seL4 and do a pull request to your own repository, it will run all the mandatory checks and the local checks and everything that doesn't need the machine queue. You have to go into settings and say, enable GitHub Actions to do that. But if you've done that, it should work. You can even, if you want to dig into it a bit more, like we've done that for Proofcraft, for instance, you can provide your own AWS keys and start up your own AWS machines, and those workflows will also just work on your own forks. A hardware queue is a bit more interesting. You would need your own SSH key to Unis.mu to make that work. And the only thing that you will not be able to do is deployments. So updating manifests and things like that, that always goes to the seL4 organization, which only the CI bot is allowed to do. So this is kind of nice. It means if you're developing and are planning to do a pull request, you can actually check all these things before you even ever get in contact with the foundation. So you can, make all the tests work and have everything nice and shiny for the reviewer to look at and make a good impression. The other thing you can do, all right, I know where the time went. I was going to click on all these links and show you that. You can use the code in the CI actions repository to run your own CI or your own local test setup. So I've tried to make this reasonably regular and hopefully understandable how these tests are set up. So on GitHub Actions, there's always a YAML file that tells you what are the parameters to the test, what does it expect as input. And then the setup for the seL4 actions is that it will always call a bash script called steps.sh, and then we'll just perform the steps, set up whatever it needs for the test to run. So if you have a fresh development machine and you want to know what to do to run seL4 test, you look at that file and you'll get all the dependencies. You can also use the Docker file, we'll already have them, but if you want to set up your own stuff, that's where it is. How much detail do I want to show you about that? There is, okay, maybe one bit. If you've ever done CI stuff on GitHub, this is a bit non-standard in the sense that you would be expected to use the GitHub, repo checkout action. These tests don't do that. They have their own script for checking out the repository precisely so that you can just take them and use them on a non-GitHub action environment. I think that's, for anybody who actually wants to screw with this stuff, that's one thing I think that they need to know. Okay, as a more normal person, what can I immediately do? So this is one of these details screens that you get when you click on the details link. And mainly, you can look at the test logs. They're kept for 3 months. I would like to keep them longer, but that's the maximum you get on GitHub. You can see what worked and what didn't work. So if it's red, it didn't work, right? If it worked, all these little triangles here will be folded in. You can unfold. This is there so that you can make sense of the log, because those logs tend to be very big, but you can zoom into the bit that failed fairly quickly with that. Okay. It also will tell you how long it took. That's sometimes interesting, but it's probably mostly interesting to me because I try to get those numbers down. They're important for feedback, right? If you put up a PR, you don't want to wait half a day to see if everything worked or not. Okay, the other thing you can do is you can look at build artifacts. And build artifacts are basically things that the test action leaves behind. So in addition to the logs, which is just the output of the test, This could be, for instance, the PDF of the manual. So if you ever want the current reference manual for the current development version of seL4, you can look into the test run for RefMan, and the PDF will be there. Other things that are left in there are, for instance, the benchmark results. So in a lot more detail than what is up on the website. Things like Isabel images, actually not the images, just the database. The images are stored on AWS. Yeah, that's probably what most people will want to use. But the way to get there, I should probably say, is for this one, it's important to click on this summary bit in this GitHub Actions panel, not on the details. I haven't written the UI. I can't. I've struggled to find these a few times, but they're there. Okay. My last slide. What do we have? So we have tests that run automatically on pull requests, on every local change to the repository, and then global tests that run on changes to the manifests. The tests do automatic deployments of things. So the manifest changes are the most frequent ones, but it will also update the website, deploy to the website if you pull request to any of those. It will update the Docker containers. It will also update all the Docker containers that we use for the tests themselves, and so on and so forth. All this is implemented with GitHub Actions, AWS, and the machine queue. And compared to the test setup that we used to have back in the old days, where it was called Bamboo, I don't know if you remember the SSRG bot that would say, hey, your test results are here. In comparison to that, you get direct access to everything the test produces. So pretty much anyone can just go and look. The test setup itself is open source, and contributions are very welcome. I would, in fact, say there's a whole bunch of issues that say, it would be cool to implement this. So feel free to pick any of these. Maybe shoot me a message before you start, because I might be working on it already, but chances are probably not. Okay. Contributions welcome. Thank you.
Cool. Thank you, Dylan. Are there any questions? Ooh, let's start. Good talk. I'm wondering, I haven't checked in a few months, but is there any guidance on like the documentation on how we should be contributing tests? Because last I checked a few months ago, I think it was just if you make a kernel change, you should update seL4 test, and that was about it.
Yeah, that is about it. It's okay. That is a fairly wide topic because it depends on what you're changing and what you want to do. So you can contribute to the test infrastructure, and this is mostly just concerned with setting up those tests, starting them, how do I interact with them, and so on, but not the content, what they're testing. What would actually be the most pressing right now would be updates to seL4 tests to increase the coverage and make them slightly less flaky. There's a few tests where there's something in the test setup that is not quite right. They sometimes fail, and they sometimes succeed, and that is a very bad test.
Mm-hmm.
If you're concretely interested in some of these, I can try put up more documentation on that.
I guess maybe I mean more generally like where to look if you're submitting a feature for a specific repository, right? It's not especially clear like, you should be checking out these tests and you should really be adding something because you have a new feature.
Yeah,
I guess is more what I mean.
Cool. Yeah, that's definitely something we can do.
Can you also clarify that not just seL4 tests, but also like integration tests in like the VMs or something like that?
You want me to clarify what exactly?
So if you're adding a new...
Sorry, I'll give you the microphone.
Just watching it.
Test. If you're adding a new feature, so say an SMSQL mechanism, then adding tests to seL4 tests, gives you like the unit test coverage, but then having an implementation in like a VM and having a test that we can actually have an integration test to make sure that if it ever breaks, we'd at least catch it is like what I'd say is the bare minimum. And also it's much easier for reviewing because then you can quickly check out the test and run it and from there see what it's like.
Well, so a formal answer to the question of which test should I look at is there's this file that says if I change this repository, these are the tests that I need to run. And for seL4, that's all of them. So that's where you would add.
So one of the things that we're interested in that I mentioned yesterday is having an assurance argument that documents where all the assurance evidence lives. And so this seems like a good source of information to say, okay, I'm using this version of the kernel, and here's where the proof evidence lives, or I know that the proofs have been run on that version. What would I be looking for there, like the existence of the image or some of the status things that you were displaying on that screen that says, oh yeah, this passed its test, or the proofs ran and haven't been broken in this current version? Or what would be a good thing you think maybe we could just point to in the assurance argument to say, oh, the proofs are correct, and here's how I know, because look in this repo and this is the version I'm using?
I would say for that specific application, I would say the default XML files of the collections that are
And then we can just
relevant.
parse that and say, okay, all right.
Yeah, and it'll say exactly this revision, and from the update date, you will see when the proof was run.
Yeah.
And it will only get updated when the proof was successful.
Okay, cool.
Yeah, if you want more detail, you can query the GitHub API, but that's probably more persistent.
Where to look.
Yeah, exactly.
Some hands over here.
I don't have experience with formal verification, but I have had the experience of trying to informally prove claims that are false before I realized they were false, and it always involves hair pulling and backtracking. And I'm wondering if you can talk a little bit about the experience of finding bugs in the kernel during the kernel verification process, and where in the process you find them, and if that's something you try to minimize, and if so, how you decide how much effort and resources to put into less rigorous kinds of evaluation, like testing and like comprehensive auditing and stuff before you do the formal thing.
I would say the level of pain is testing, review, proof. So that's roughly how you want to invert that in terms of time. So if, for instance, for the AH64 proofs, we would, of course, run the tests on Ken's pull request. We would then spend quite a lot of time on reviewing it and writing the specifications first, syncing up all the specifications, which gives you also another source for finding bugs. It's a bit like, different people go in different rooms implementing the same algorithm. Already just writing those specifications, if it's not the same person, will uncover some bugs. And only after all that process, we would start the proofs. Because, yeah, that is the most painful time to find out.
I can imagine.
Is there another hand around here somewhere?
Hey, so the proofs are the slowest part of the test suite, or is that not right?
I don't think so anymore. seL4 test is probably, well, okay. The collection of seL4 test and the rest, which all is necessary to, like, if you want to do a release, you first get all the images, then you get seL4 test on hardware, and then you get CamKIS and all the rest. So the collection of all of that will be slower than the proofs. Each single one is faster than the proofs.
Okay, which brings me to the second question. Proofcraft is working on writing new proofs. Is there any concern about how long those will take to run, and is there any way to make them any faster, or are we at the performance threshold? Basically, we can't get faster proofs.
We have a little bit of headroom in both directions. So, of course, at Proofcraft, a lot of the stuff we're doing is trying to make the proofs faster and leaner, and not just based on rerunning everything, but trying to make them more modular. That is hard work though, and takes time itself. The other headroom we have is the hard timeout at 6 hours, and we're at 4, so that's fine, right? And also, of course, we're using concurrency. So adding a new architecture doesn't slow down any of the other proofs. It'll just add another set of VMs.
Just to go off Sultan's question, so have you spent any time looking into the performance of Isabelle itself, or just the L4V proofs?
Spent any time in like the last 20 years, or?
Yeah,
Yes,
I
mean, yes, we have multiple times. In fact, I still have an issue from Kent where he says this one proof takes longer than all the rest together, and I still need to fix that. But Isabelle is actually pretty fast. It's like if you compare it to other theorem proving systems, it's had concurrency support forever, basically. Well, not forever, but for more than a decade. And that is really what makes a difference, being able to spread the proofs over multiple cores. Well, that's why there are 16-core VMs. That makes a huge difference.
Might be getting into the weeds, but
Microphone, please.
This might be getting too much into the weeds, but isn't a lot of the time to run the proofs spent in doing GC in the ML runtime? And so is there any advantage to someone putting research into making a better GC?
I would. So I don't think so. I mean, there is GC, but you can see, like, if you make the test logs more detailed, if you go to the next detail level, it's 50%. No, it's like 2% or something. The GC time will vary drastically with the amount of memory you have and the amount of memory you give the VM, and what parameters you give to Isabelle, how large a heap is allowed to get. So if there's memory pressure, then yes, it will burn all of it in GC. But if you set it up that it has plenty of memory, it'll be fine. It will not be a huge overhead.
Last question.
I think Raf is burning to say something about that.
So on the Isabelle performance front, I don't think you'd worry about GC except when it interactively gets stuck and you have to wait for it. But if you really want to improve Isabelle, then I got access to a machine with many, many cores once, and it was a huge disappointment to find anybody using Isabelle in this room do not use more than 8 cores. It will take the exact same amount of time using twice the amount of CPU. So that would be the key step. Like if we get another go at a machine with 50-something cores, and we ask, hey, Isabelle, use them all, then we could change our proofs to also use more cores, and we'd actually get more throughput. But at the moment, it's like 8 cores, and if you want to use more, you have to run something entirely different on the side, like another architecture.
Yeah, so that is the way around that, right? You run multiple different proofs on that same machine. So,
Can I just make one last point? Yeah. So you don't think there's anything else you could do other than chucking more hardware at it?
there's things that could be done, but I don't think we're the people to do it.
Okay.
Like, I mean, you do not want to screw around with the kernel of the prover, right? Performance is not the main issue there. The correctness is.
All right, I think we should wrap up there. So let's thank God. Go on.
Thank you. So we have a 15-minute break. We're a bit flexible, so let's start at 11:05. And we'll start again here where Anna will explain the different